a research fellow at MIT. He is a prolific researcher in theoretical physics and cosmology, with over 160 citable papers and more than 11,000 citations. His recent work has been at the very forefront of investigating the topics he will discuss today, including the Hubble tension, modified gravity models, and evolving challenge to the ΛCDM framework. So please go ahead, Professor.
Okay, thank you for the introduction. It's a pleasure to be here with you today to discuss some interesting issues about in cosmology. Please feel free to interrupt me whenever you want to ask any questions. Of course, there will be also questions at the end. But during the talk, I would be very happy to be interrupted for discussion of or other questions. What I'm going to talk about...
This meeting is being transcribed and summarized.
What I'm going to talk about, so today, I'm going to summarize perhaps the main tensions of the standard cosmological model, this ΛCDM, and I'll review the current status of measurements and models which have been suggested to address this tension and therefore extend the standard model ΛCDM with new degrees of freedom. So the structure of this talk will be the following. First, I will give a brief history of the standard model changes and the ΛCDM model. I will discuss in particular the various standard model changes that have occurred during the last several hundreds of years and see how cosmology has changed over this large amount of years. Then I will discuss the four main classes of tensions which currently appear in the standard model, and they are inviting us to invent new degrees of freedom to extend this model. I stress that such extensions have occurred several times in the past, so perhaps now we're at the edge to discover new degrees of freedom of the standard model, which will further extend it and make us discover new physics. Now, the tensions I'm going to discuss today, even though these are not the only tensions that exist, are the Hubble tension, which is well known, the growth tension, the baryon acoustic oscillation tension, which suggests the presence of dynamical dark energy based on the new DESI data, and the cosmic dipoles tension, which seems to challenge the fundamental cornerstone of cosmology, the cosmological principle. Then I will briefly discuss towards the end a possible new degree of freedom that may need to be incorporated in the standard model to make it consistent with many of these tensions. And this is in fact a proposal we have made during the last years, which involves the presence of modified gravity, a new degree of freedom as an approach to the resolution of tensions of the standard model, modified gravity manifesting itself at late cosmological times, and I will discuss about this during my talk. Now let's try to learn from history and try to think what happened during the several thousands of years, actually, when humanity had to change its view on cosmological model, to understand what happens each time that this changes and how could we learn from these changes. Now, perhaps the first major contemporary, I would call it, change of cosmological model was shifting from the geocentric model, which assumed that the Earth is in the center of the universe, to the heliocentric model of Copernicus, which happened about the 16th to 17th century. And it was the various advancements of technology and telescopes which allowed this change. It was realized that, for example, the retrograde motion of the planets and the phases of Venus and the moons of Jupiter, which were made us understand that we live in a solar system, and in the center of the solar system exists the sun, and it's not the Earth that in fact is in the center of the universe. It's the sun which is in the center of the solar system. And in those days, the universe was practically consisting mostly of the solar system, while the stars was not clear what they actually are. Now later on, this actually was also known much before, that in fact the sun is the center of the solar system, since Aristarchus of Samos in Greece, in ancient Greece, 310 to 230 before Christ, it was realized using some more simplified observations that in fact it's the sun which is the center of the solar system. But then it was rediscovered with more detailed data and technology by Copernicus and replaced the the geocentric system of Ptolemy. Then from the heliocentric system we shifted to the infinite universe in the 18th, 19th century, when technology was able to understand that the stars are not just divine objects, but in fact part of the universe, which have a distance from Earth, which is huge. And this distance was measured using the so-called stellar parallax geometric measurements. Later on, it was realized by Einstein that this infinite universe has to be static because of symmetry. Einstein actually invented the fact that since there is a special symmetry, homogeneity in the large scales of the universe, it could also be time symmetry, and suggested the static universe, for which he had to introduce this cosmological constant, which is a repulsive gravity, to counterbalance the attractive gravity of matter, and therefore create a static universe, which was proposed in the early 20th century in the context also of general relativity, which at the time was in its birth, in its first steps. Later on, it was realized that in fact Einstein's cosmological constant and the static universe was in fact an oversimplification. It was actually incorrect, and Einstein called it one of his biggest blunders. It was realized by Hubble and Lemaitre that first of all general relativity had a solution for an expanding universe, which was very natural, and by Hubble it was understood that data, the galaxies, were receding from each other, from Earth at least, and also from each other if we live not in a special time place in the universe. And so it was realized that the universe actually expands, and that was the first solid evidence for the expansion of the universe, which was later on extended to include some physics, some temperature, all the known species of particles, and it was extended to include inflation and also light elements, the cosmic microwave background, inflation theory. These were all ingredients of the so-called Big Bang cosmological model, which was essentially an expanding universe, which was supplemented by physics, by real physics, which had to do with the particles that existed in this setup. So this was developed in the 1960s and 80s. Later on, a new ingredient was introduced in this Big Bang model, which is dark matter, which was introduced because of the observed galaxy rotation curves, which implied that there must be more matter than is actually seen. So this was called dark matter. And this, there are also gravitational lensing and galaxy clusters, where the motion of galaxy stars clusters revealed through gravitational interactions that there is much more matter than is visible. So dark matter had to be introduced to supplement the Big Bang theory. And more recently, in the late 1990s, it was realized that in fact one more new degree of freedom, one more new ingredient had to be introduced, and this was the repulsive gravity on very large scales, which was called dark energy, and this could be implemented by negative pressure. And the simplest way to introduce repulsive gravity, which would cause accelerating expansion of the universe, would be to use the cosmological constant. And in fact, from the 1990s, late 1990s until now, this cosmological constant remains in fact the standard model of cosmology. It has passed most, but not all, cosmological tests and observations. It's consistent with a huge amount of observations, so it's a very powerful model, despite the very small number of parameters it has, only 6 parameters. And so it has been a very robust model, but recently, as I will argue, there have been some tensions which seem to shake this model, and some of those are the Hubble tension, for example, the S8 growth rate tension, which has been weakened recently, but may still exist, even though in a weaker nature, which indicates that perturbations grow at a much weaker rate than predicted by general relativity and the initial perturbations. The cosmic dipoles tensions, which indicates there are some very persistent anisotropies on very large scales, where the cosmological principle would predict that we should have a homogeneous universe. There seem to be some dipoles which persist in very large scales. The CMB anomalies, which are some statistically significant anisotropies, which are not completely consistent with the statistically homogeneous cosmic microwave background. The ISW integrated Jackson tension, which seems to give some stronger anisotropies than expected due to the integrated Jackson effect. The lithium problem, which there is some missing lithium compared to what nucleosynthesis predicts. In fact, there are 3 times less lithium in the universe than what nucleosynthesis predicts, even though nucleosynthesis is very successful in predicting all the other elements. But for lithium, there seems to be some problem when it comes to predicting its abundance. Now, all these tensions are described in some detail in a review I have written with my former student Fotinis Kara, which is called Challenges for ΛCDM and Update. We summarize all the tensions in some details, about no more than 100 pages, where we summarize all the tensions of ΛCDM, standard models, and try to unify them in a way to point towards new kinds of models. Now let me review the standard model, ΛCDM, just briefly. We have, first of all, the cosmological principle, which implies the Robinson-Walker metric, which has a single parameter, a single unknown function, this A of t, which is the scale factor. This is the function we want to know from the background. There is also the curvature k, which has 3 values, maybe open, closed, +1, -1, or 0. Currently, data from the CMB and other data imply that k equal to 0 is perhaps the most likely value for the curvature. We live in a flat universe, where we actually have to observe and find the scale factor A of t of the Robinson-Walker metric. Now, this is obtained using plugging this metric in the Einstein's equations. We have the Friedmann equations, we connect geometry, the scale factor and its time derivative, with the density and the curvature, and also the acceleration equation, which connects the second derivative, time derivative of A, with the density, the pressure, and the cosmological constant. And notice there is a minus sign here, which tells us that normal matter can only lead to deceleration of the expansion, while the cosmological constant and also some dark energy with negative pressure could in fact lead to accelerating expansion. So the fact that we see accelerating expansion implies that there is some repulsive gravity term like the cosmological constant here. And also there is the rate of change of the density, which is connected with the density and pressure and the Hubble constant through this relation, which also comes from this. This is not independent, it comes from the other 2 equations by just differentiating with respect to time, this first Friedmann equation, and using this other equation here. So these are the 3 main equations which are not independent, which allow us to study the expansion of the universe and connect observations of A, of the scale factor, with theory, with the properties of the density and pressure. For matter, we have the density of matter scales as A to the -3, and using the 4 known energy components, or of course there may be more, but at least those we think that exist. The radiation component, which scales at like A to the -4, matter, which scales like A to the -3, curvature, which is almost 0, but it would scale like A to the -2 if it existed, and the cosmological constant, which constant density, doesn't change with time. So this is then rho critical here would be this expression here, and omega is the density over rho critical, the critical density, the density we would need to have for flatness of the universe. Now the redshift gives us defined by the ratio of the wavelength of radiation we observe over the wavelength that is emitted by faraway galaxy, which is the ratio of the two scale factors, the present scale factor over the scale factor at emission, and this we call it 1 plus z, where z is the redshift, and therefore by measuring the redshift we can know at which scale factor the light was emitted here. Now the standard model has this h of z, the standard model has this form here, h0 omega 0 matter 1 plus z cube plus omega 0 r for radiation, r plus z to the fourth, plus this cosmological constant contribution, which for flatness is of the form 1 minus omega 0 m minus omega 0 radiation. So this is another model, and we're going to test this. And how do we test it? We have to make measurements, first of all, of the scale factor, because the scale factor here at h of z, because h of z is connected with the scale factor, has to be measured and then compared with the right-hand side. That's how we proceed. We measure h of z, and then we compare, then from h of z we can fit the other parameters, omega 0 matter, omega 0 radiation, and the cosmological constant. Of course, if this h of z that we measure cannot be fit with these three terms, then we need something else, some other form of dark energy. So the idea is to measure h of z and then find all these parameters, omega 0 matter, this constant parameter, omega 0 radiation, and see if in fact we get a good fit. If we can get a better fit with something more complicated, I mean significantly better, because if you have parameters you always get some slightly better fits, but the question is to get significantly better fit, then we need to change our cosmological model. So the first thing is to measure h of z and see if it can be well fit in the context of ΛCDM. How do we measure h of z? We need to measure distances, because the Hubble parameter is connected with distances in cosmology. Distance in terms of redshift can give us the Hubble parameter in terms of redshift again. And I will show you right now how it's obtained. Let us consider, for example, one particular type of distance, which is called luminosity distance. And to measure this distance, we need something called standard candles. Objects which have known absolute luminosity, known power, they emit a known amount of power of radiation. These are supernovas. This is our best standard candle, and some gamma ray bursts also could be standard candles, but not very accurate. Now, supernova is a white dwarf star which absorbs matter from a companion star, and when it crosses the Chandrasekhar limit, then it immediately explodes through a huge explosion, and this happens at exactly the same mass at the Chandrasekhar limit. When it's crossed, then gravity becomes very much stronger than the pressure that supports the star, the white dwarf, and then the explosion happens at a very huge amount. It increases for a brief amount of time. These supernovas shine as much as a whole galaxy for some days. So it's extremely powerful explosion. It can be seen from very far away, and also it's an explosion which has a very well known luminosity. So if we know the luminosity, the absolute luminosity, the power of radiation that is emitted, we can estimate the distance to this supernova using this kind of relation. You see here, this is an observer, this is the distance, and this is the object that emits. We have here the intensity of radiation, that is power per unit surface. This is the power emitted, which is known for standard candles, and this is spread over the surface of a sphere from 4 pi dl square. And if we can measure the intensity, if we know the emitted power, we can measure this dl, the distance to the supernova, and this distance dl is connected with the Hubble parameter. It can be shown using this integral from 0 to z of the Hubble parameter. So if we measure dl at various z's, at various redshifts, at various scale factors if you want, then you can have parameterization of h of z. You can fit for h of z using this equation, provided you can measure distance. So measuring distances and also redshifts, of course, we can measure the Hubble parameter. This here is a generalization of the Hubble's law. If you put slow redshift here, let's say z which is much smaller than 1, then this relation becomes exactly the same as Hubble's law. It becomes h of z times d equals c times z, which is exactly Hubble's law. But this is a generalization of the Hubble's law because the Hubble parameter in general is not constant. It's h of z. It depends on the scale factor, the rate of expansion of the universe. Now, the standard candle we can use is gamma ray bursts and type 1a supernovae. And astronomers usually do not use the absolute luminosity and the intensity L, the apparent luminosity. They use the absolute magnitude and the apparent magnitude M, which are connected with L, small l, and capital L through this logarithmic relation. So it's a matter of convention, historic reasons have introduced these logarithmic terms, the apparent luminosity, the apparent magnitude, the absolute magnitude, which are connected with these two luminosities. This is just, I will be using this in the rest of my talk, so be prepared to know this connection. Another way to measure distances is using the so-called angular diameter distance, using which can be measured through standard rulers, that is, objects which have a known size, not a known luminosity, not a known power, not a known absolute luminosity, but a known scale, known dimension. And the most powerful such standard ruler is the so-called CMB sound horizon, cosmic microwave sound horizon. The distance sound waves have traveled from the Big Bang until the time of recombination, when the first atoms were produced in the universe. And if we know the size of this, the scale of this sound horizon, which you see here, and if we measure the angle by which it is seen through our telescopes, then we can essentially deduce the so-called angular diameter distance through this triangle here, which is a very small theta, of course. For such a very small theta, we have the relation that dA of z, the distance to the ruler, is equal to the sound horizon scale, the scale of the object we know its size, over the angle over which we observe it in the sky. And this measured quantity, the angular diameter distance, is connected again with the Hubble parameter through this different integral. It can be shown using the Robinson-Walker metric, that this equation is true. And so if we can measure dA for various redshifts, we can also fit and find the Hubble parameter h of z by putting this, by measuring this at several redshifts. For small z, again, this becomes the Hubble's law, because this 1 plus z becomes 1 over the denominator. This becomes z over h0, the present time of the Hubble parameter. So we have h0 times dA of small z is equal c epi z, c times z, which essentially is the Hubble's law. So this is also generalization of Hubble's law, but using now not luminosity distance, but the angular diameter distance. And we can use this sound horizon scale both at low redshifts, where it's protected through the Barron acoustic oscillations, and at high redshifts, where we see it directly through the CMB perturbations spectrum. Now, how can we use the standard candles in some more detail to measure h of z in practice? So the idea is to find h0 and h of z, of course, using standard candles, using measurements for z less than 0.1 if we want to measure h0. So we have this relation here, which connects the apparent magnitude with the absolute magnitude and the luminosity distance, which is the same relation that I showed in the previous. It's like the same, it's this relation here, but written in terms of absolute magnitude and apparent magnitude through these quantities here. So we write it this way. We we replace dl of z through the Hubble parameter using this integral, and we define the Hubble free luminosity distance by multiplying this dl by h naught. And using these definitions, then the measured apparent magnitude is equal to the absolute magnitude, the absolute luminosity in logarithmic terms, plus the logarithm of the luminosity distance, the Hubble free luminosity distance, plus the logarithm of the Hubble parameter 1 over h naught times c, plus 25. This has to do with the units, because we use here megaparsecs. We have to put a 25 here because of the definitions which have to do with these quantities. So in this expression, this is the crucial expression to measure h naught. And to do that, first of all, we rewrite this equation as the apparent magnitude is equal to 5 times log h dl plus this calligraphic m, which involves this term m and this logarithmic term, which has h naught, which is this definition here. And we measure this directly through our telescopes for the various objects like the supernovae that we see. We also measure this locally by using various calibrators, the so-called distance ladder method we use. I'm not going to have time to describe it in any way, in any detail. So we measure this using distance ladder methods. We measure the absolute luminosity of supernovas, or the absolute magnitude of supernovas using these methods. And once we know these two objects, we can fit this luminosity distance using a cosmographic expansion, like expanding to powers of z of the redshift, and fit for h naught. So we measure it for various smaller redshifts. This equation here for dl is valid for smaller redshifts. That's an expansion in powers of z, so it's valid for smaller redshifts. And so if we know all the other things here, we fit for h naught and for this q naught, which is the deceleration parameter. So we fit to data to various supernovae at smaller redshifts less than 0.1, and we find and fit h naught. This is the rules of the game. This is how we find h naught in practice, using this exact relation. Now, the thing to notice is that there is a degeneracy between h naught and m, the absolute magnitude. So if we have not measured locally correctly this m, the absolute magnitude, then we will get a wrong value for h naught, because you see these two are degenerate. These are both the only two constant terms in this equation. So it's important that what we measure is their combination in the Hubble flow. But if we don't measure m locally correctly, we have made an error in h naught. So it's important to understand this degeneracy between the absolute values of supernovae, the absolute magnitude, and h naught. Now, if we want to go to higher redshifts, we can fit for hz at cosmological parameters at higher redshifts and obtain the cosmological form for h of z. Fit this, minimize chi-square of this form, where we have this mth using this expression up here. These are the observed absolute apparent magnitudes divided by the error. And so we minimize this chi-square with respect to two parameters, this calligraphic m, which essentially is the combination between m and h naught, and omega zero matter, the cosmological parameters. So when we put in this dl now not just an expansion, we have to put the full expression from the cosmological form of h of z, and so we come and fit for omega zero matter and whatever other parameter we have using the full cosmological expansion in the Hubble flow. Now, let me now try to look a little bit on the baroacoustic oscillations in the cosmic microwave background. This is, of course, as you know, a homogeneous and isotropic radiation where we are embedded, and it was created when the first atoms formed. Initially, photons were scattered in a plasma. At some point, when the temperature dropped, the atoms were formed, and the photons free stream. They come to us directly and bring to us a picture of the universe as it was at the time when recombination happens, when the atoms form. So it's one of the earliest times of the universe where we have actually optical image of what happens. This was first, this image, this picture of the universe was first detected by the satellite COBE in some big detail in 1991. At first of all, the spectrum of this background is a black body spectrum because it's generated by this equilibrium between photons and plasma, and it's extremely homogeneous when you have a resolution of about 1 degree Kelvin. If you come to higher sensitivities, you see a dipole which has to do with our motion with respect to the homogeneous and isotropic system of the cosmic microwave background, the preferred frame of the universe, where the cosmic microwave background is homogeneous and isotropic. We see the dipole, our velocity with respect to this frame. If we subtract this dipole, then we go down to delta T over T times to the -5, and we will see the primordial fluctuations which led to the creation of galaxies and structure. Now, the sound horizon is an important scale here, which is the distance that sound waves have traveled before up to the time of recombination. Before recombination, plasma was coupled to photons, as I showed in the previous slide, and because of having the pressure of photons and the gravity of plasma trying to collapse and the photons were putting pressure, we had an oscillation effect, a sound wave induced by gravity and the pressure of the photon, and there were expanding spherical sound waves emanating from baryon gas perturbations and driven by photon pressure. Now, at recombinations, the photons free stream away and pressure becomes negligible, and so these spherical sound waves freeze, and they define a specific scale, a frozen scale in the universe, which is called the sound horizon at recombination. It's this scale that we can measure today using both the large-scale structure, because it depicts on the large-scale structure, and also directly can measure it through the CMB, cosmic microwave background power spectrum fluctuations, through the various peaks that exist. Now here you see a picture of what really, see here the coupled of the reddish photons and gas and the plasma. You see when the photons free stream away, then the gas remains fixed at the particular radius of the sound waves, and then the black, which is dark matter, accretes on these baryons, and this is depicted on large-scale structure. You see this same again. You see that initially they are coupled, gas and photons are coupled. The photons decouple here. The gas, the plasma, the sound wave remains fixed, and then matter accretes on the sound wave. So this is a quick way to see that. You can see it also in 3D motion, in 3D view. Here you see the spherical sound wave. See it expands initially outwards, but then it freezes when the atoms form because the photons stream away. And this happens on various centers on the last scattering surface. And each one of those spherical sound waves exists independently, and they define a scale on the last scattering surface when the atoms form. And these circles, these scales, accrete baryons, they accrete dark matter afterwards, and they form galaxies. See, galaxies form, in addition to their own spectrum, using this type of spectrum. And you see, as galaxies form on these spherical shells, they define a specific scale which can be measured through the correlation function of galaxies, and they have a peak. And so there is more correlation on this particular scale. If we measure all distances between galaxies, we find a specific scale which corresponds to the sound horizon scale, and we can measure this both directly on the last scattering surface and through the large scale structure as baryon acoustic oscillations. And so this measurement of distances provides us another way to measure the Hubble parameter, because if we measure distances, we can measure always the Hubble parameters through these integrals I showed previously. So this is this baryon acoustic oscillation peak, this scale. This is the angular separation, which corresponds to the scale of various redshift slices. And if we know the angular separation of this scale, we know the scale, we know the angular separation, we can measure the angular diameter distance and connect it to the Hubble parameter h of z, and so we measure h of z at various slices of large-scale structure, at various z slices of the large-scale structure. So this is a very powerful way to measure distance and therefore measure the Hubble parameter h of z at various redshift slices of large-scale structure. Very powerful method. In fact, it has been used extensively, and recently we had very good results from DESI, an instrument which is specifically designed to measure the large-scale structure, redshifts, and galaxy position, and find this Hubble parameter. And very nice results came out, which I will discuss later in this talk. So how can we use the standard ruler, the sound horizon, to measure h of z? We have the sound horizon of the recombination, standard rulers in the early units at the time of recombination. So it's like measuring this scale here, this RS, the scale of sound horizon. We measure this angle to this sound horizon, and then we can measure this distance, this angular diameter distance, dA, at a redshift equal to about 1100, which is the redshift of recombination. So we measure this angular scale. We're also using the peaks of the CMB power spectrum, for example. The angular scale of sound horizon is on these peaks, on this peak, the first peak. We can also measure it through the sound horizon, through the band acoustic oscillations at lower redshifts, at redshift maybe 1 or 1.5 or 0.5. So we have the same object, the sound horizon, measured at various redshifts, the largest of which is the redshift of recombination. We calculate RS because we know how much distance the sound horizon has evolved from the Big Bang. This is from 0 to t, the time of decoupling. CS dt divided by also by the scale factor because we want the co-moving sound horizon. And after a change of variables from time to the scale factor, we get this form. So if we know h of a, the Hubble parameter before recombination, we can deduce it, assuming that there is only matter and radiation at those times. There shouldn't be anything else. So we calculate it assuming that there is only matter and radiation before recombination. This is the most probable scenario. So it depends on the density of baryons, density of photons, and density of cold dark matter. And so if we calculate RS, we measure theta s, we can deduce dA of z, which is the angular diameter distance, and RS is calculated to be about 147.6 megaparsecs from the Planck estimate of the baryon density, etc. And so we express dA of z in terms of h of z, which is equal to h naught times E of z, which is the second part of the Hubble parameter, without the Hubble parameter here. And we have we put in E of z the standard model form for h of z, and we can deduce the value of Hubble parameter h naught. In this way we can infer it, but here we assume that we know RS, and also that we know this integral, which has to do with the expansion rate in the context of the standard model. So we assume lambda CDM here. We assume that we calculate correctly RS, and then we infer h naught, and this is found to be much smaller than what we measure locally. That's the Hubble tension, basically. So we can do the same with the baryon acoustic oscillations, which corresponds to redshifts, to lower redshifts at large scale structure, at theta s, theta bow, and RS we have the we have the baryon acoustic oscillation redshifts. So notice that there is a degeneracy between h naught and RS, which means that if we decrease RS, we can increase h naught. How can we decrease RS? We can assume there is early dark energy at early times, and in that case we can add new fluids to make h naught bigger and RS smaller, and make it more consistent with local measurements of h naught, which show h naught bigger. So we can also deform E of z and also increase the denominator, and also increase thus the measured h naught, which is another way to increase h naught. Now the question is, so it's clear that because there is a degeneracy between h naught and m, we can also express the h naught tension as an m tension, which means that there is a difference between the magnitude of supernova we estimate. We have this relation I showed before, theta s equal to h naught rs over this integral, where RS is this integral here. If we assume that Planck provides the correct E of z, and we plug in the RS from the sound horizon, this form, we find this H naught, which is the H naught, this low H naught from the Planck satellite. And if we assume that this is the correct H naught even for local measurements, we have this calligraphic M estimated through the Hubble flow. We plug in this for H naught here, and we deduce M, the absolute magnitude of supernova, and we find this minus 19.4, which is different, smaller than what is actually measured locally from the distance ladder methods. We have a different luminosity for supernova, and so it's like measuring different luminosities of supernova from the CMB and from the local measurements of Cepheids. So anyway, this is so using the distance ladder, we can measure the M. We can also measure the calligraphic M from the Hubble flow, which is the combination with H naught, and we can deduce the local value of H naught using these relations here, assuming that the absolute magnitude that we measure locally through using the distance ladder is equal to the luminosity of supernova on higher distances. Then we get this kind of value for H naught, which is different from what we get from the cosmic microwave background. You see, we have this, and this actually is the well-known Hubble tension. We have different measurements using the CMB and the local measurements of the distance ladder. And this is the Hubble tension that I mentioned before. The key point is that this M depends on the effective Newton's constant. And if there's an assumption here that there's no change in the Newton's constant before and after the time, the redshift 0.01 when we enter the Hubble flow, because at lower z we have peculiar velocities, and it's not clear that we have a Hubble flow existing. So one hypothesis one can make here is that the absolute magnitude of supernovae has changed from its local value to the value that we obtain using the inverse distance ladder from the CMB, and this would imply a transition of the luminosity of supernova from a local measurements to the Hubble flow, and this would resolve of course the Hubble tension, but of course it would require also some kind of change of the properties of supernova at exactly this redshift between the local measurements through distance ladder and the cosmological measurements in the Hubble flow. Now, it's possible to achieve this change through a scalar tensor theory, because these are theories which allow for modification of the Hubble of the Newton's constants through this non-minimal coupling here and this potential. And through the dynamics, for example, if you have a first-order phase transition, you would have a change of the field phi from a false vacuum to a true vacuum. This would modify the gravitational constant at various regions of the universe, and so we could have locally one value of Newton's constant, and outside of our bubble have a different value, and this would induce this change of M from the local region where we are inside the bubble to outside of the bubble of the first order phase transition through this first order phase transition. So we would have different kinds of magnitudes of the supernova. So we would have these bubbles and would induce. Alternatively, we can have a quiescence-like behavior, a rolling phi, and a discontinuity of f of phi at a particular location. This would change f of phi, and it would also then change Newton's constant, and would also change the supernova magnitude, leading to the resolution of the Hubble tension, because it would lead to different luminosities of supernovae at various at exactly a critical redshift, which divides the local value of M, of the absolute magnitude, to the Hubble flow value of M. Now, so how do we resolve this problem? One possibility, of course, is the one that I just mentioned. Usually there are other possibilities. Here we see the Hubble parameter evolved through Z using the CMB parameters and the locally measured value, which is the value from the distance ladder of the group of shoes. And you see that from the CMB we get to a different value than what we measured locally. And so this disagreement here is essentially the Hubble tension. So this is distance ladder edge of Z using M calibration CIFFU at Z less than 0.01. This is a local measurement. And the question is, how can h of Z derived from late time calibrators become consistent with h of Z derived from early time calibrators from the CMB and BAO sound horizon? One possibility is, as I said, to change the intrinsic luminosity of supernovae and then thus change the measured value of H0, which would correspond to bringing this point down. And this would be also consistent with local other measurements, one-step measurements, which do not involve distance ladder. The other way is to change the sound horizon. In that case, this curve would go up and become consistent with this point of local measurements of H0. And the third way is to deform this H of Z and make it consistent with this local measurements of H0. But in that case, we would have first of all problems with the fit of the BAO data. This data here would not be as well fit. See, these are the BAO data that you see here. And also, they would not become consistent with one-step measurements, which do not involve distance ladder. And also, they would not be consistent here with the other measurement of supernova, which of course is a schematic. These are not real data, it's schematic data, because of the calibration of supernovae, they all would be above the sound horizon scale calibration, and so even if we deform it, we can hit this point, but we will miss all the other points of the supernova and most of the others, which are calibrated using distance ladder measurements. So this deformation approach is not very efficient in resolving the Hubble tension. The other two I mentioned are much more efficient. Now this brings me now to the other tension, the S8 tension, which I'm going to briefly describe. Now for a decade, a second major tension existed, which is the so-called growth tension. It is a conflict in the clumpiness of the modern universe. So we measure a parameter which is called S8, which is the combination of sigma 8, which measures the amplitude of fluctuations on scales of 8 megaparsecs at the present time, times the square root of omega matter over 0.3. This is just a convention, the 0.3. So this gives the omega matter is a driving force for the growth of fluctuation, so it should be there in the clumpiness parameter measurement, and sigma 8 has to do with the amplitude. So the combination of the two give us this S8 parameter, which measures the growth strength, the strength of growth of fluctuation essentially, or the clumpiness of the universe, how strong is the growth of fluctuation. And the conflict is the following: early universe predicted this Planck ΛCDM fit. If we start from the CMB fluctuations and evolve forward using general relativity, we find a strong growth. We find an S8 of 0.83 plus or minus 0.01. And however, at late universe, the actual surveys which measure directly this parameter without predicting it from the primordial fluctuations of the CMB, they found a much lower value, 0.76. This was from lensing measurements and other measurements like weak lensing, which measures the bending of light, actually the distortion of the galactic shapes due to lensing, the redshift space distortion, which measure peculiar velocities of galaxies, and the cluster counts, how many clusters are present at various redshifts. All these types of measurements allow us to measure the clumpiness of the universe, the strength of growth, and they all led to lower, weaker S8 than the predicted S8 from the CMB. So this was the significant 3 to 4 sigma discrepancy until recently. And recently it became clear that this tension appears to be resolved because new data show that the previous measurements were probably due to systematics or incomplete data. And the most recent weak lensing data from KITS and DES year 3 data converged now to a higher value of S8, 0.181, which is in excellent agreement with the Planck CMB prediction. Now this seems to have disappeared. At least all the latest weak lensing data are now consistent with the with the CMB. So this tension seems to have disappeared as far as weak lensing data is concerned. And the new cluster count data also seem to point out to a higher value of S8, and which is in excellent agreement with Planck. And so there is no tension now anymore, no growth tension with respect to the CMB, at least with respect to most recent data. Here you see some contour plots for this sigma-8 parameter with respect to omega matter, and you see these are the CMB prediction, and the weak lensing prediction now seem to be much more consistent with the CMB. And also the same with cluster counts. This is the yellow part, is also consistent with the Planck CMB with other measurements. So this S8 tension seems to be now the more or less weakened, if not disappeared. So we can focus on the surviving tension, which are the rests. Here you see the growth tension as it was before, the previous data. You see there were lots of measurements indicating a weaker S8 than predicted by Planck. But now this, of course, the latest measurements now are very close to Planck, so it seems like this tension has disappeared. And also here you see the conflict between the early time measurements of H0 based on the CMB and the late time measurements, the distance ladder measurement actually, which show a discrepancy of the Hubble tension up to about 5 sigma. Now another tension is the so-called cosmic dipole tension, and this has to do with is the most fundamental tension. It does not challenge lambda, the cosmic or the cold dark matter, but the foundation of ΛCDM, which is the cosmological principle, the isotropy, the actual metric of the universe, which is the most important assumption we make. Now, the largest anisotropy we see is the CMB dipole, which we know it's due to our velocity. So this is not a primordial feature. It has to do with our velocity with respect to the CMB frame, which is where it will be homogeneous and isotropic on the average. It's interpreted as a simple kinematic effect. Our solar system is moving with a velocity about 370 km per second relative to the cosmic rest frame. So if the CMB dipole is purely due to our local motion, then after correcting for it, if we subtract it, the sky map of all other objects would appear perfectly isotropic. However, there seem to be, even if we subtract this dipole, we go to a frame which should be, everything should be isotropic, we see bulk flows. We see very large and persistent flows of velocities, peculiar velocities, on particular direction. And this is a paper by Watkins et al., which show that this is the most important plot here, the lower right, and the bulk flows seem to increase with scale instead of decreasing. This is red, is the prediction of ΛCDM, which is decreasing. Is not only much smaller, but is decreasing with scale. The actual observation is bulk flows which are much bigger, up to 300, up to 400 and more kilometers per second per megaparsec, and seem to be increasing with scale. We're averaging out the velocities on various scales, and we see there is coherent flows in particular directions, which are shown here. And the probability for this to happen randomly is extremely small. It's something like 10 to the minus 4, 10 to the minus 5, you see here. So it's a very unlikely statistical effect. It's probably something strange happening on very large scales, maybe a new kind of fundamental anisotropy which would violate our cosmic metric. So this test seems to fail. In fact, there are other data like independent studies of distant quasars and radio galaxies, see these samples here, which are not isotropic on very large scales. They exhibit their own cosmic dipole in number counts. There are more quasars in one part of the sky than the opposite part. And so this observed quasar radio dipole is misaligned with the CMB, and has a much larger amplitude than expected from lambda CDM. So if we take into account the CMB using our CMB velocity, our velocity with respect to CMB, we would expect to have some apparent difference of numbers because of our velocity. This is a relativistic effect. But here we see a much stronger dipole than expected. And here, in fact, you see the observed dipole, this red line here, magnitude of the dipole, with respect to the expected dipole we would expect based on the fact that we are moving with respect to the isotropic frame. So we would expect to see a dipole, but now we see a much stronger dipole of quasars, many more quasars on one side of the sky than the opposite side. And this is the direction of this dipole. And so the question is, what causes this kind of fundamental dipole? Because we're talking about a very large scale. So it's very unlikely to have happened by chance. And also radio galaxy dipole exists also in a similar direction. And you see here the predicted CMB value of the dipole, this dashed line, when we subtract various rings of radio galaxies in the sky. And you see that both of these surveys, this NVSS and the TGSS survey of radio galaxies, indicate much stronger dipoles than expected based on the CMB, as far as the distribution of radio galaxies in the sky exists. There are many more radio galaxies on one side of the sky than the other, than expected in the case of for the CMB. So this is challenge to the cosmological principle, and if the universe is not isotropic, the FRW metric is wrong, and our entire cosmological framework is flawed. So the question is, what would cause such a fundamental anisotropy, and what would be the correct metric to use on these large scales? This is an open issue in cosmology right now, and we are not exactly sure if our metric, our fundamental assumption of the Robson-Walker metric is correct one. And here you see the various dipoles which exist. This is dark flow dipole for the velocity. This is the NVSS direction, the cut-wise direction for the quasars. This is the radio galaxy. And you see that many of them are very close to the sky. This is on the opposite direction, the same dipoles. So it's puzzling to understand what actually causes all this. So these are the bark flows, QSO dipole, and the radio galaxy dipole. The worst, however, the most recent tension is the so-called Desi-Bau CMB tension. And this is a new and powerful tension, which is emerging from the recent dark energy spectroscopic instrument DESI data, which measures the barn acoustic oscillations at various redshifts, and so it can plot for us this H of Z with very big accuracy. So if we can measure distances using the baryon acoustic oscillation standard ruler, the sound horizon, we can plot H of Z in very big detail, much more detail than before. Now, when the Desi-Bau data is combined with other primary data sets, like the CMB from Planck and the supernova from Pantheon Plus, the standard lambda CDM model is a poor fit. So this H of Z I showed before from lambda CDM is a poor fit. So we need something else. It looks like the equation of state parameter for dark energy is not equal to -1, does not correspond to lambda CDM. H of Z does not correspond to what we expect. And there is some dynamical dark energy. This omega lambda is not constant. It has some dependence on redshift. And this is the equation of state parameter W of Z, shown favored by DESI instrument. You see there is a dynamical effect. The W equal to -1 corresponding to lambda CDM, and the cosmological constant is a poor fit. And the best kind of fit is crossing this line W equal to -1. And here you see the H of Z, and also the Hubble tension is worsened because this dust line is the best fit value of H of Z, which hits H naught at an even lower value than CMB. It's at 64. The H naught is going to be about 64 compared to the local measurements of 73, which is over here. While the CMB, the Hubble tension from CMB is 67 kilometers per second per megapascal. So it is even lower. So it worsens the Hubble tension. This dynamical dark energy here is such that this deformation is in the opposite direction we want to resolve the Hubble tension. So this thing is not only we have dynamical dark energy, but we have in a direction dynamically in a direction which worsens the Hubble tension. This is a very big puzzle right now in cosmology. And so this new dynamic dark energy model in GR worsens the Hubble tension by preferring an even lower H naught. You see here the best fit H of Z, assuming only DESI and the CMB, is hitting at about 64, the Z equal to 0. So the theoretical implication is that for this are what? First of all, if we stay in general relativity, a standard scalar field which is called quiescence with Lagrangian, the usual scalar field Lagrangian which is of this form, has an equation of state of this form here, and this equation of state is always larger than -1. It cannot cross the -1 line because we have a positive kinetic term, and so you can easily show that this form for a positive kinetic term can never become smaller than -1. So it can never be phantom. It can never be in this region here that you see in this plot, which is measured. See, it measures W of Z equal to -1.4 at high Z. So this cannot be predicted in the context of general relativity for a quintessence scalar field. To get a W less than -1, the field must have a negative kinetic term. And such ghost fields are considered pathological because of very instability. And even worse, cannot even cross. It's very hard to cross this line in the context of general relativity and scalar fields which are coupled minimally, that is just coupled through gravity. So a single scalar field in general relativity cannot smoothly evolve from W larger than -1 to W less than -1, like shown here. So this data is hinting at physics forbidden by standard general relativity and quintessence models. That's a very strange situation. And so the core problem is that there is this problem. So we have written recently a paper, a couple of weeks ago, where we propose a new solution based on modified gravity scalar tension theory, where we allow the gravitational constant to evolve with the scale factor. So we use this unjudged here, parameterization for the evolution of the ratio of G effective over G Newton. So G Newton is the local value of G, and G effective is the cosmological value at various scale factors. And this is in this paper we have recently written here, and you see this 2511 reference here. And we find the best fit of which seems to be evolving, but then going back to general relativity at both the present time and at very early times, because this is the parameterization we used. And we find also that W of Z, the equation of state, and H of Z are different from the ones DESI would predict in the case of general relativity. We fit, of course, to the DESI data, and we find because of the new degree of freedom, this W becomes a bit different, because actually the data are the G is also evolving, and so we have a difference in WD as we would expect with this data. So this is the Lagrangian of the scalar tensor we would need. We have where F to phi is the non-minimal coupling, U to phi is the scalar potential, and the problem and the scalar field solution allows us to reconstruct this U of phi and F of phi, and find in that case that we can viably cross -1, W is -1 without having any problem with our theory. So we have made a fit and found a new value of H naught, which is much more consistent with the local measurements than it would be in the case of general relativity. So this is one approach which could resolve this problem, and we can reconstruct also the F of phi using this equation. I'm running out of time, so I will proceed a bit further. So these are the best fits for F of phi, non-minimal coupling, and for U of phi. You see here. So we have this is the current status of tension. The SA tension is actually resolved. The Hubble tension is potentially diminished using this modified scalar tension theory we have proposed. The DESI-Bao CMB tension is also explained in the context of modified gravity, which allows for a phantom crossing dynamical dark energy, which would not be allowed in the context of general relativity. However, the cosmic dipole tension in the context of these models persist unless we have a first order phase transition, which I showed in a previous slide. Now, the main points of this talk I wanted to stress are the following. First of all, the standard lambda CDL model is a simple and successful model that is consistent with the wide range of cosmological observations. Second, a few tensions of the model parameters indicate the possible presence of new physics. And third, there are three main classes of models that have the potential to replace lambda CDM in the context of these tensions. And the late time modified gravity, which we propose, constitutes a potentially interesting approach to the resolution of these tensions. Thank you very much for your attention. This is the end of my talk. I would be glad to answer any questions if there are any.
Thank you very much, Professor. So let's move on to questions. So, what you please would ask?
So I cannot hear you very well.
Hi, can you hear me?
Yes, I can.
Okay. So, if anyone have a question, please go ahead.
So,
Hi, we can hear you.
oh, you can hear me. Thank you.
Yes.
Okay. My question is about the Hubble tension that you alleviated using scalar tensor theories. So I have read before that in order to get alleviation of the H0 tension in those theories, as you get a larger value for H0, which so you alleviated the tension and you got a larger value of H0 for early universe. Is that right?
Actually, this H0 comes because we allowed for dynamical dark energy at late times. And we did this, this is not an early time solution. I mean, many early time solutions try to implement modified gravity at early times, so they change the sound horizon scale. In our approach, we have used a late time introduction of scalar tensor theories, which deform H of Z, and at the same time, they resolve the Bausch-CFB tension from the DESI data, because the DESI data have introduced a very powerful constraint, a very powerful new tension in the problem, which deforms H of Z in the opposite direction. But if you put modified gravity there, and if you fit to all the data, you can actually resolve both at the same time, the Hubble tension and the DESI Bau data tension, because these two seem to be incompatible
Yes. So you are actually resolving the tension for both early and late time universe.
Actually, both the DESI data are late time, because the DESI data are time at late time, so they are both late time tensions, but different tension. One is the H naught tension. The other is the dynamic dark energy tension. Now, the early time resolutions of the Hubble tension are different. They just change the sound horizon. We don't touch the sound horizon. For us, the sound horizon is fine. I mean, we don't touch the CMB. CMB is a beautiful, a very well tightened data set. So we don't touch it. We assume it's okay. We don't touch the recombination physics because we think that this is a very robust physical setup. We understand many things there. So we don't touch it, but we touch late times. And we touch them in a specific way by introducing a new degree of freedom, which is allowing the Newton's constant to evolve at late times, but evolve in such a way it remains consistent with constraints. We have tested the constraints, the G dot constraints, and so we are very careful to see that we remain consistent with it. So as G effective changes, two things happen. First of all, we have a modification of the H of Z, and also we have a modification of HC0. And these two are in such a way so that we both resolve the Hubble tension and we allow for dynamical divergence that crosses the W equal to -1 line. Because you know, what you obtain is a crossing of W equal to -1. This you cannot do with any theory in general relativity. You have to put something in, and modified gravity is the simplest approach. Now this is a fact.
Sure, yes.
Shows crossing W equal to -1. You have to do something about that. If you believe it. If you don't believe it, you can do other things. But if you believe it, you have to do something. And the simplest thing to do, touch gravity, modify gravity. If you modify gravity, then everything is smooth and can be achieved. You can achieve crossing of the W equal to -1. If you don't touch gravity, it cannot be done. Quintessence cannot do it. That's simple.
Okay. Also, another question goes to the F that you reconstructed for this theory. Did you propose it first, or how did you find the analytical expression?
Good question. We actually numerically found the f of z and u of z and then we found f of phi numerically using the data. So we start with the data.
Okay.
We see the q of z. You use the DESI data, the CMB data, the Pantheon Plus data, growth data. We put a lot of data in there to fit for both q of z, which we used various parameterization of the equation of state parameter. We used, for example, CPL. We used various parameterizations. More or less, they all agree with the form of q. Q of z is the Hubble parameter square over h naught square, and mg is the g effective over g Newton. So we have basically found the best fit of these parameterizations, q of z and mu g of z. And using this best fit, we go back to the scalar tensor cosmological equations and solve these equations for f of z and u of z. Because if we know q and mu g, we can solve this differential equation and find f of z and u of z. And also there's another one which shows phi of z, the scalar field tensor of z. We eliminate the redshift and find a numerical, essentially, form of the function f of phi and u of phi. And then we ask the following question: what analytic function can reproduce well our numerical reconstructed from the data form? And then we try various functional forms, and we find that these forms here are very close to what the data told us, because the data told us a curve. We didn't tell us a function. And then we go and find a function which closely mimics what we find directly from the data and from the numerical solution of the differential equations using the numerical forms of q of z and g effective over g naught of phi. So these are essentially best fits of simple functions to what the data told us. The data told us a line, just a curve for f of phi and u of phi. What simple function can reproduce it? The simplest we could find are these forms. So this is the way that we reconstructed and found those forms. These are really fundamental functions which, however, are derived from the data. The data tell us that these are good, the simple and good fits.
Okay. And you made those fits by, I don't know, maximizing likelihood or MCMC method?
Exactly. We maximize likelihood. We tried various functional forms which maximize likelihood with what the data tell us. And this seemed to be, of course, we could use very complicated forms, but we used simple functions, various types of simple functions. And after trying hard, we found that these are the best simple functions that can reproduce the curve obtained from the data for f of phi. Because the f of phi gave us a curve, didn't give us a function. Because it's just the data and using this parameterization. We have these parameterizations here, q of z and mu g of z. From this parameterization, we got the f of z and u of z and phi of z. And then we obtain this fit. Is it clear?
Yes. Thank you.
Thank you, Marco. Anybody else have a question? Maybe You can write it in the chat box. I don't know.
Me, I have a question.
Okay, please go ahead.
Yeah. Is there alternative models, do you think? I mean, alternative models to the LCD, Lambda CDM, that you consider most plausible for simultaneously resolving the H0 and S8 tension?
Okay, in my opinion, the most promising models to resolve this is something which will be fundamental, understood. I mean, you can do various things with parameterizations, with various couplings, dark matter, dark energy, but then all these things are phenomenological and not really fundamental. The only really fundamental approach one can have in these directions is using modified gravity and in particular scalar tensor theories, because in this way you know where your fields come from. In other case, you just put parameterizations which you don't really know the fundamental, there are no simple fundamental physics there. So, in my opinion, one should try to understand these tensions through fundamental physics, and in particular, the simplest modified gravity models we have, which is scalar tensor theory, or even Hordensky models. If these are not good enough, we can go to more complicated models, but we have to be fundamental. We have to understand where our field phi comes from, where the scalar field comes from. The only theories where we know where the scalar field comes from is modified gravity theory, scalar tensor theory. There we know that phi is nothing else but essentially the Newton's constant generalized. We have a non-minimal coupling. F of phi is nothing else but 1 over 8 pi gn is the Newton's constant. It's a fundamental constant of nature. It's not just an arbitrary field that we invented just to do a thing. It's something that the nature already has given to us. So it's important to try to think in terms of fundamental physics when we want to solve the tension. So I would personally, that's why I also did these works. I personally think this is a good way to proceed, to look at modified gravity theories consistent with constraints that can address this tension. And also, nature itself told us, because you know this. If you look at you see what DESI data told us. They told us this W has to cross the minus the phantom divide line. How can you do it with general relativity? You cannot do it with general relativity. You have to go outside of general relativity. Quintessence cannot do it. So nature itself told us, go outside of general relativity. So it's not only the fundamental kind of approach where you need really a theory which is physically motivated and not an arbitrary scalar field, but also the data. The data themselves told us, go outside of general relativity. So I think it's a clear hint to move in this direction. I'm not saying that we have the right theory. I'm just saying that in principle, this is the direction I personally at least, would like to see the resolution evolve towards something fundamentally and physically motivated. Is it clear?
Yeah, it's clear. Well, maybe that's what I'm going to say is a little philosophical. I don't know, but I understand that these models are being, were being constructed here on Earth and based on data that we see or we saw on the cosmos, right? When we saw the stars and we made some measures. Do you think, or well, I don't know, what do you think about that when if we travel to another place in the cosmos, very, very far, if we, well, I don't know, what do you think? If we see or we measure something different from our theories, maybe, what do you think about this, what I'm thinking?
Yeah, that's an interesting point. I mean, as I said, also the data tell us some interesting things in that direction. I mean, the cosmological principle, if it's respected, would tell us that wherever you go in the universe, you would see the same things, because the Copernican approach to the cosmological principle. I mean, it tells us that all observers in the universe are not only equivalent, but they are also seeing on large scale the same thing. But you see, there are some recent data, which these cosmic dipoles, which seem to also challenge this approach. I mean, there may be maybe the universe is not the same everywhere. I mean, maybe there is if these dipoles are true, this cosmic dipole, the quasar dipole, for example, or the radio galaxy dipole, or the bulk flows are indeed not statistical fluctuations, but are real facts, then it means that there is fundamentally the universe is not homogeneous and isotropic on very large scales. And this means probably that maybe there are some preferred directions or preferred observers in the universe which would see different things compared to other observers, perhaps. So it's a matter of right now our theories would, I mean, the obvious question I would tell you in the context of the cosmological principle and the Copernican approach, which are all observers are equivalent, would tell you, in fact, everybody would see similar, would deduce similar conclusions, all observers in the universe. But these dipoles tell us that maybe there is a problem in that. I mean, maybe on the larger scale, the universe has preferred directions and therefore preferred observers. So I'm agnostic in this direction right now in view of the new data. Unless, of course, these data are shown to be flux, statistical fluctuations, or systematics. But something strange is happening on very large scales. We don't know what. These dipoles are extremely peculiar. What they mean, where they come from, what breaks symmetry, what breaks the symmetry of isotropy and cosmological principle. If it does, it's right now a big puzzle of cosmology. It's one of the tensions. As I said, that there are 4 tensions I mentioned, there are more. If you see our review article, you will see more, but I selected these 4 as more interesting. In fact, the latest one 2 years ago it was not present, so it's not in our review. The DESI dynamical dark energy tension is not in our review because it didn't exist 2 years ago when we wrote the article. So this is an update I told you today, which includes the latest tension. But in one of them, which we describe, is the cosmic dipoles. And I don't know the answer to your question. It is probably, I mean, a standard cosmology would tell you everybody sees the same things because of the cosmological principle. But nowadays, I cannot be so sure. Is it clear?
Yeah, we have to go to those places to test it, right? We cannot do it in our lifetimes.
Or we can either assume that the universe is homogeneous and isotropic, so that means every observer is essentially the same. Or we must understand where do these tensions come from, where do these dipoles come from. If we understand where these dipoles come from, then we will be able to say what each observer will see. Because if we know the metric of the universe, we can see where the dipoles come from, then perhaps we understand the whole metric of the universe. Then perhaps we can predict what each observer will see by seeing this full metric. But now we are not completely sure what is the metric of the universe on very large scales, and therefore we cannot be sure exactly what each observer will observe. In the context of cosmological principle, they will observe the same. But again, as I said, we are not sure about the metric of the universe on extremely large scales. So it's not an obvious. We don't have to go there. We have to understand what these dipoles tell us. We can say, sit here on Earth, understand the universe better, and then predict what each observer will see. Right now, the simplest thing is that they all see the same. But as I said, until we understand these dipoles, we cannot be sure. And if we understand them, we can predict what each observer will see.
Okay. Thank you.
Thank you, Simon. So we have time for another question. I think there are no more questions. So thank you for the presentation, Professor Leandros, and we hope to see you again.
Thank you very much. It was very nice to be here with you. It was a pleasure to be here. And I hope we meet
Thank you.
again in some meeting or somewhere else.